Welcome back to the classroom. My name is Mr. Wong, and today we're going to be looking at the 2013 HSC Physics paper. This is going to answer Module 7, Inquiry Question number 4, which is about special relativity and obviously the nature of light being Module 7. So in this question, we're looking at a nuclear reaction. We have uranium-235 going through transmutation with a neutron, and it makes barium. We have also krypton and 3 neutron isotopes forming from this reaction. So this is what we talk about mass defect and mass energy equivalence. So let's have a look at what we need to do to approach this question. Okay, so the first question we have here says, use the data above to calculate the energy released in this reaction. Okay, so what we need to firstly demonstrate is energy. What we know is there is going to be a mass defect. Now the mass defect that's going to happen is what it's saying is the mass that we have here in total here is going to be slightly different to the mass total that we have here. Any difference in that in mass is, according to Einstein's equation, E equals to mc squared. Any difference in that mass was converted into the kinetic or the energy of the system. So that's actually how mass and energy can be equivalent. Okay, so in this case, we are given atomic mass units. So we're going to use a slightly different formula to this to calculate the energy released. But let's have a look. So we have the mass before. So we have mass before. That is the uranium, so 235.0439 plus 1.008665. So that's the mass, and then our mass after is the barium plus the krypton plus 3 nitrogens. So I'm just going to quickly plug those numbers into the calculator, and then we'll calculate mass defect. So what I have for the mass before is 236 minus 0.52565, and the mass afterwards. What you can already see here, there is clearly a difference in the mass before and after, and that's what we know as the mass defect. So the mass defect is the mass before subtracted by the mass after. So whatever mass we have before subtracted by the mass after, we have an overall mass defect of 0.18587 atomic mass units. So obviously in this scenario here, to use E equals mc squared, this form that we have here, we need mass to be in kilograms. So you can convert that into kilograms. Just remember, 1 atomic mass unit is equivalent to, if I have a look at the formula, 1.661 times 10 to the power of negative 27 kg. So you could times it that way and then apply equals mc squared. Or another way of doing it is use the mega electron volts formula. So it would be 0.18587 multiplied by the value of 931.5. Okay, that's going to give our value in mega electron volts, because the units for this one is mega electron volts per c squared. So the end value I get is 173.9 1.137.905 mega electron volts. And that's how you do the question. Moving on now, we go to question B. It says, apply Einstein's idea of the equivalence of mass and energy to explain the production of energy in the reaction above. So again, what I mentioned there is from the nuclear reaction, there is a mass defect when the sum of the mass before and after for the reactions are added together. So when the sum of mass of reactants are subtracted, by the sum of mass of products. This missing mass, according to Einstein, was converted into energy. Okay, and that's effectively how we can explain what happens in nuclear reactions. In all nuclear reactions that we see, even in the production of energy from the sun, is through the process of where the mass defect changes, disappears, and that mass disappearance is then converted into the energy using Einstein's idea of E equals mc squared, and that explains the relationship between energy and mass. So hopefully you found this video useful in explaining the mass energy equivalence, and also how to interpret radioactive equations to derive value for energy production. If you enjoyed the video, hit the like and subscribe button, and I'll see you next time.